Groups attached to the benzene can either give electrons to the benzene or take electrons away from the benzene. If they give electrons to the benzene, we're going to call them electron donating groups. Another name for it, activating groups. These electron donating groups normally they are connected to the benzene by a heteroatom, and that heteroatom has a lone pair. So you can see over here that these lone pairs, since they are directly connected to the benzene that is conjugated, they can give electrons to the benzene by resonance. These three groups over here, they are strong electron donating groups with the OH and the NH2 being stronger than the OR. Donation of the electrons will increase the nucleophilicity of the benzene. So it's going to make the benzene more nucleophilic. Electron donating groups, they are divided into strong activators, moderate activators, and weak activators. All of these activators, they direct the ortho and the para position, the stable you are allowed to have in the exam. To know if groups are strong activating groups, you need to look at the lone pairs and the lack of the carbonyl. So you shouldn't have any carbonyl in there, just lone pairs. And all of those, they have lone pairs. Okay. The OR is a strong activating group, but it's going to be the weakest among all the strong activators. Now, when the carbonyl is present next to the lone pair, this is going to decrease the strength of the activating group now. And the activating group is going to become a moderate activating group. And these are the examples of all the moderate activating groups in there. For the weak activating groups, these are any sp3 hybrid carbon or any benzene. Weak activating groups, they have no lone pairs to donate. They only donate electrons by inductive effect. For example, over here, if I have a CH3 that is connected to the benzene, then this is going to donate electrons by inductive effect due to the difference in the electronegativity between the sp3 hybrid carbon and the sp2. The electrons are pulled through the sigma bond towards the sp2 hybrid carbon, and that makes this CH3 an electron donating group by inductive effect. It is a weak activating group. Same thing over here. If I have a phenyl group that is connected to the benzene, since both carbons are sp2 hybridization, I will still have a pull of electrons through the sigma bond towards both of these cycles in there. Term weak, we give it to groups that don't have lone pairs and they are attached to the benzene. There are two groups. It's either an sp3 hybrid carbon or a phenyl group that is attached to the benzene. Both of those, they donate electrons by inductive effect. All activating groups, whether they are strong, moderate, or weak, they do direct the ortho and the para position. Let's have an example in here. Let's say if we have a benzene and we have a group on the benzene and we want to introduce a second group on the benzene, where this second group should go. It depends on what is the substituent on the benzene. So here the substituent is a CH3. That is a moderate activating group, and that activating group directs the ortho and the para position, meaning that my electrophile over here that is made up from the reaction of the HNO3 and H2SO4, this is the nitronium ion. So that nitronium ion is going to add ortho and para to the CH3. I do have two ortho positions that are the same, and I have a para position in there. Okay, these two ortho positions are the same, so I'm going to end up getting just one product on the ortho position and one product on the para position. So you're going to have two products in there, and this is how you write them down. So I'm going to have a CH3. I'm going to have the NO2 added ortho to the CH3 plus the NO2 added para to the CH3. Always the para product is going to be the major product. And the reason why it is major, because the groups are the farthest away from each other. And the ortho product is going to be a minor product because of the closeness of the CH3 to the NO2. Another example over here, if I have an OH on the benzene and I'm doing Friedel-Crafts, remember the limitations of Friedel-Crafts reaction. Friedel-Crafts does not happen with a strong activating group like an OH or NH2. These are the only groups where Friedel-Crafts does not happen with as strong activators in there. So over here, I would end up having no reaction. OH and NH2, both are unique because they are very strong electron donating groups in there. So whenever you are brominating or nitrating, you have to pay attention of the amount of nitration and the bromination that you're getting in your product because they are very strong activators. They are going to direct all the positions at the same time. Notice here that the CH3 was a weak activating group. It's an electron donating group and it's a weak one. So with this, you're going to end up getting the ortho alone and the para alone as a product. But with the OH and the NH2, and these are the only two ones that are very strong, and this is the reaction that happens with them. Whenever you are brominating or nitrating, then you're going to nitrate all the ortho and the para positions at the same time. Also, you're going to brominate all the ortho and the para positions at the same time. So here I'm going to end up having a tribromo product for both, in order to limit the reaction in there, in case you don't want all the ortho and the para positions to be halogenated, then in this case you would need to work with the Lewis acid and make the Lewis acid less reactive. To make the Lewis acid less reactive, instead of using iron bromide, we simply use iron, just iron, or we can take away the iron and use just the bromine in there without the iron. And the reaction can happen because those two are very strong activators. So in this case, you're going to end up getting the ortho product alone and the para product alone. On the other hand, electron withdrawing groups on the benzene, those they pull electrons away from the benzene. And when they do that, they are going to make the benzene more electrophilic than a nucleophilic. So they are going to increase the acidity of the benzene. So if you want benzene to be more acidic, then you have to introduce more electron withdrawing group on it to pull electrons away from the benzene and make it more electrophilic. Now, these electron withdrawing groups on the benzene, they normally pull electrons away from the benzene by inductive effect. All electron withdrawing groups, they have either a partial positive charge or a positive charge on the benzene. So here, for example, nitrogen has a solid positive charge. You have to draw the Lewis structure in order to determine the charge of the group that is connected to the benzene. Whether it is a solid positive or a partial positive, that will make the group an electron withdrawing group in there. So these are examples of electron withdrawing group. Any carbonyls, any sulfonates, any cyanides, all of those, they carry partial positive charge on the atom that is directly connected to the benzene. And those, they are going to make the benzene more electrophilic by withdrawing electrons from the benzene. All electron withdrawing groups, they direct the meta position. And electron withdrawing groups, if we go to the table over here, they are divided into a moderate deactivating groups and a strong deactivating groups. These are electron withdrawing groups. We also call them deactivating groups in there. These are all the moderate deactivating groups. Normally, the moderate ones are the ones that have carbonyls directly connected to the benzene. It's either carbonyls or a double bond O or a triple bond. These are the moderate ones in there. And all of those will be connected to the benzene with their partial positive charge carbonyl. Okay, this one over here is partial positive, and this one is partial positive as well. Now, for the strong deactivating groups, these are the nitro group, the ammonium group, the carbon trifluoride, and the carbon trichloride, CF3 and the CCl3. All of those four, these are very strong deactivating groups. Normally, deactivating groups, which are electron withdrawing groups, these are meta directors. So they direct the meta position. Let's have an example over here. So we have the carbonyl directly attached to the benzene. The carbonyl is partial positive. So this one is an electron withdrawing group or a deactivating group. It is a moderate one. Normally the strength of the substituent that is attached to the benzene, if there's only one substituent, we don't care about the strength. But if there are two substituents in there, then this is when we care about the strength of these substituents. So now if you want to introduce the Br positive from this reaction, the brominium ion, then in this case, the brominium ion is going to add meta to the carbonyl. So we're going to end up getting only one product in this case, where the bromine is going to add meta to the carbonyl. Remember that Friedel-Crafts reaction does not happen with any electron withdrawing group on the benzene. So here you will have no reaction. With the nitration over here, I am forming the nitronium ion. So we want to introduce the nitronium ion. Look at the identity of the group that is attached to the benzene. This one is an electron withdrawing group. Electron withdrawing groups, they do direct the meta position. And the meta position, again, is the position on the third carbon of the substituent. This is the meta position in there. So the nitro group will be on the third carbon from the sulfonate, and you will end up getting just one product in this case. This is the sulfonic acid. It is a sulfonic acid, not a sulfonate. And then you're going to end up having your NO2 in there meta to it. Now, for the case of halogens on the benzene, halogens have lone pairs and they are electronegative. So because they have lone pairs, they can donate electrons by resonance to the benzene. And because they are electronegative, they can withdraw electrons away from the benzene. So they do double a job in there. They donate electrons by resonance, and they withdraw electrons by inductive effect. Their withdrawing outweighs the donation of electrons by resonance. This is why halogens are considered to be electron withdrawing group. However, halogens, they do direct the ortho and the para position. So back to the table. Halogens are considered to be weak deactivating groups, but they direct the ortho and the para position. So to sum up, activating groups, they direct the ortho and the para position. Deactivating groups, they direct the meta position. Halogens, they are deactivating, but they direct the ortho and the para position.